Hello and welcome back. Today we're going to talk about color and resolution. This is our last of the most technical lectures that we're going to have in this class. It's also probably the most useful topic that those of you who aren't specifically going into print will find out of everything we've covered so far. Color is going to be relevant to everybody in any GIT field of study or focus area. So these kind of things apply to print definitely, without a doubt. But they're going to apply to web design, graphic design, video, photography, animation, whatever it is that you end up doing. Understanding how color works. Not color theory, not what colors look good together so much. I couldn't help you with that. I'm sorry, I'm no help in matching colors. But understanding exactly how color works is very important. So that's the topic for today. CMYK and RGB are the two color modes or models that we're going to cover. Those are the ones that are most relevant to us, though you'll see when you do your reading this week, there are a whole lot more out there. When you get into the color modes that are in Photoshop, there's grayscale and index and other things that we're not going to get into here, but be aware of those and check them out in the reading. Okay, so color modes and models, it's the exact same thing. It's just that in Photoshop and Adobe's program, they're called modes. In the real world, they're called models. So if I slip up and call it one or the other, just know that it means the same thing. Basically, color models are, like the bullet point says here, ways of converting colors into numbers using a mathematical formula. So really, based on the physics of light waves, how can you make, I don't know, yellow out of red, green, and blue? If those are the three colors that you have available to you, how do you make all those other colors? So RGB, we have millions and millions of colors that exist in the world. We can see those with just three primary colors, red, green, and blue. So how does that work? That's what a color model does for us, is the system that explains how color works. So without getting too deep into it, that's kind of the basis of it. We're going to move on from models from here a little bit, but first off, we'll just talk about the big ones. So RGB is additive color. If you remember nothing else from this lesson, remember that RGB is additive and CMYK is subtractive. Now what that means is that the more light you add in RGB color model, the more color you get and the closer to white. So if you want more red, you add more red light. If you want more red in CMYK, then what you do is you subtract out all the other wavelengths of light. That may sound like a lot, but it'll make a lot more sense once you watch some of the video, especially some of the YouTube videos that I posted on additive color. LAB is a conversion space, so it's very broad. Mathematically, it's not based on necessarily three colors like CMY or RGB. It's based on a luminance value, brightness value, and then A and a B are just different axes on a graph where you can map out all different colors of brightness and darkness and hue and saturation and everything. For our purposes in this class, we're not going to get into LAB really at all. Just know that when you convert from RGB to CMYK, LAB is the conversion space in between. So mathematically, it makes sense for our software to take the RGB values of our photo and convert them to LAB and then to CMYK instead of directly. All right, so the basis of CMYK, you guys I think understand from last week. That should be pretty straightforward to you. Red, green, and blue, I believe is pretty self-explanatory too from what you know in other classes or this one that we've covered already. But if you look at the image over on the right-hand side, you'll see what is it's just a graphical representation of color gamuts. So lab color, LAB, is larger, physically larger, what you see in that graphic. Adobe RGB is a little bit smaller. sRGB, CMYK is down inside of those, really small. We'll talk about gamut later on, but just be aware that you have different gamut depending on which color mode or model you're working with. All right, so here's what we mean a little bit more about subtractive and additive colors. On the left-hand side, you see RGB. Your screen on a monitor or TV or your phone, when it's off, it's black, right? When you turn it on, it's emitting light. Those little diodes of your screen or LEDs or OLEDs or whatever your screen technology is using, CRT TV, if you have that old technology, it's blasting light out at you. It's emitting light, so it's emissive color. And on the other side, when you put ink on paper, what's happening is the pigments, the physical properties of those pigments or dyes or inks are such that they absorb different wavelengths of light. They're filtering it out. So when you see cyan ink on paper, what you're seeing is the cyan light being reflected, which is a combination of red, green, and blue wavelengths. It's in those additive color videos. We'll get into that. You can get into that on your own. But just know that when you look at printed material or color in the real world around you, what's happening is different materials, they're going to absorb more light or less light. And whatever wavelengths of light bounce off of that material instead of being absorbed, that's what you're seeing, and that's what you perceive as its color. So in Arizona on a hot summer day when the sunshine's been shining all day on a black car or your black leather seats in your car, they get really, really hot. Black is absorbing a lot more of those wavelengths of light, and that is being transferred into heat energy, of course, so that's why it gets hot. A white car, it's also absorbing pretty much equal parts of the visible spectrum, but it's reflecting a whole lot more of it. So it's not absorbing some of the red and some of the green and a whole lot of the blue. What would that give you? That would give you yellow, because there's a little bit of red and a little bit of green there. Anyway, hope I'm not going too fast. This should make a lot more sense when you do the reading, but I wanted to just illustrate what subtractive and additive color are together here. Here's another example, a couple of different images to kind of drive the point home. On the left-hand side, over here, let me just use my cursor. So over here, this is a flashlight with a colored gel over the lens, and if you shine red light and a separate green flashlight and a separate blue flashlight, you'll get these exact mixtures of colors. There's the yellow, the magenta, and the cyan, and then where all the colors overlap, it's white. And in the photo studio, we do this regularly. We'll put different colored gels over our lights and then shine it on a white background and illustrate this point. It's a little more difficult to do online without a video of setting that up, but I don't have that for you right now. On a piece of paper, when you add an ink or a dye or a pigment or paint, what's happening is it's laying down a layer of material that is going to absorb certain wavelengths of light and then reflect others. So in this blue area right here, where magenta and cyan overlap, what's happening is it's absorbing everything except light in that blue spectrum, and that's what's bouncing off and hitting your retina. Okay, so these other charts over on the left, RGB versus CMYK, just kind of show gamut. It's not that horseshoe shape that was on the last screen, but kind of the idea is that you have variable gamuts depending on the different color mode that you're using. RGB is stronger in, obviously you have more colors available in green, reds, and blues, and cyan is weakest in the green, reds, and blues, but it's got the most color in cyan, yellow, and magenta. All right, so ink on paper, subtractive, right? Everybody cool with that? All right. So moving on, gamut. I told you we'd talk about the definition of gamut. Gamut is just a word for saying how much color is in a certain system. So if we print on newspaper, hopefully you guys have all seen a newspaper before. Think to, maybe it's in the samples that you guys have collected as some newspaper. Look at the newspaper and look how desaturated the colors are, how low the contrast is, and overall how poor the quality is. The white isn't white, it's gray because the paper is gray, so you can't have white without white paper. And the black isn't black because the paper is really absorbent and black would just sink in and spread out. And so you can't put so much black in there that is really dark and rich. You end up with kind of low contrast, low saturation, not very bright, vibrant colors. That's an extreme example of the challenges of CMYK. There's not as large of a gamut or wide of a gamut of colors that are available to you when you're printing in CMYK. If you get a really high-end quality, expensive RGB monitor, then it's going to display, for example, 100% of the Adobe RGB gamut. And that means that everything inside that triangle, Adobe RGB, is going to be visible on your screen, theoretically. So that's nice because you have more colors available to you. The challenge is that if you have, let's say, a photograph on your screen with a really bright, vibrant greens, this landscape or plants or something like that, if you're going to print that on newspaper, what's going to happen is there's going to be a transformation in colors. Somehow you have to convert from one gamut to the other. That's where color spaces come in. They help us out with transforming between different modes or models. Definition here, bullet point says a specific implementation of a color model. That's kind of a generic definition, but basically what it means is we take RGB, for example. That's the color mode or model. And then we have Adobe RGB. That's a color space within the RGB model. Adobe RGB is just a specific implementation of color values that Adobe, among other companies, came up with and said, here's a standard. We can work within it because they're known values. It's a set gamut. It's independent. It's device independent, I should say, because that doesn't rely on a specific type of device. It's not geared towards working best on a certain type of device. That may make more sense if we talk about what a device-dependent space is. So sRGB, for example, is another standardized color space that is based on the colors that are typically close to what a monitor can do. So a computer screen, a monitor, your phone, a TV, things like that. For the most part, they're going to be close to sRGB. Next one down, Grackle. These are all acronyms. Grackle, I can't remember exactly what that stands for, but all those letters mean something. Grackle is a CMYK color space that is device dependent somewhat. It's not for a specific device, just a specific type of devices like digital presses or offset presses. Below that is SWAP, or Standard Web Offset Press, or printing. Can't remember the P actually. But there are different varieties of each of these, Grackle, SWAP, and so on. And each of these are just kind of generic spaces that say within CMYK, these are the colors that a certain device can hit. This is the gamut that this type or class of device is capable of printing to. All right, so now we're going to break this down even further and talk about working spaces. Now, I want to point out first, in your reading, when you get to that, you're going to find, if you look closely, there are two different PDFs. I won't tell you which ones. You come across this on your own, I'm sure, but they're one that says to work in RGB if you're going to go to print, and another one that says never work in RGB if you're going to go to print. So let me explain what I mean by working spaces here, and I'll tell you my philosophy, and you can see from the reading that there are different opinions out there, and you can make your own based on what you know. So a working space is, it's a name in Photoshop. You can set a working space, but basically what it means is when I'm creating a document, when I'm designing in Photoshop or working in InDesign or working in some other program, I have my content, my photo, for example. And that photo is going to be an RGB image when it comes out of the camera. I can work on that in Adobe RGB, and that means that all the colors that I work on are going to fit within that Adobe RGB gamut. When I output that, it's going to convert to something else. So let's say that I'm a photo editor for a newspaper that actually still prints, doesn't just go online. And so I'm going to take these photos from my journalists and I'm going to prep them for the press. And so they're going to go to a very compressed gamut, a very small gamut for newsprint. But RGB is going to be my working space. I prefer to go that route because it gives me more overhead. I have more flexibility in colors. I have more accuracy. It looks better on my screen. And honestly, I'm just picky like that. I like to see it with all the vibrant colors that are there. And then I can make a choice about how that gets transformed later. We'll talk about that in a second. ProPhoto RGB is another one. It's a color space that is even bigger than Adobe RGB. So when you bring in a digital a raw file from a digital camera, for example, that's closer to ProPhoto RGB, there's a whole lot of color information within that file. sRGB is a smaller gamut. I can jump back to the other slides here and show you. So sRGB down there, little bitty box, it's close to CMYK actually. It's an RGB mode, but sRGB is a color space. I wouldn't use it as a working space necessarily unless you know for a fact that you're only going to be designing for web. And that's it, because your content's only going to go there. But still, I would recommend working in Adobe RGB. If you ever just are unsure what to do, just work in Adobe RGB and you'll be okay as long as you know what a delivery space is. All right, so now the other school of thought is to work in CMYK if you're going to go to print. Because let's say you're going to, you know that the colors are going to be transformed, you might as well see what they look like on your screen before it ever goes to press. That way you avoid confusion or problems or whatever. My problem with that is just that, let's say you do go to print, looks great, everybody's happy, then the client says, okay, we want to go to the web now. We want to run a web ad with the same content that you did in this awesome flyer for us. Okay, sure. So you go back to your original and it's in swap, or worse yet, it's in newsprint or something. And those images just look terrible. The contrast is awful. The colors are desaturated. It's easier to start out with the wide gamut RGB working space and step down for whatever your output is, then try to go back. Because once you convert to CMYK, you can convert back to RGB, but all that color is going to be gone. So the image will look just the same. It's not going to magically restore all the color information that you threw away when you converted to CMYK. Okay, so delivery spaces. This is where we're finished our document. We're going to send it to the web. We're going to use it online. We're going to use it on a TV or a digital device, or we're going to print it. We're going to choose a delivery space based on that output. sRGB, anything that's going to go to a screen, you're pretty safe with sRGB. Go ahead and embed that color profile, and you're good. Adobe RGB is going to be kind of a specific thing. Delivery in Adobe RGB is going to depend on whether the shop that you're printing with is color managed. If they've implemented color management, which we'll talk about a little bit here, then they'll be able to handle Adobe RGB, and it'll work better that way too, because they can convert it in-house using their own color knowledge of their own equipment and get the best possible results for all the reasons that we talked about on the last slide. If your print shop doesn't know or doesn't tell you or just says CMYK and doesn't give you any specifics, then you're going to choose something simple like swap, standard web offset printing. But again, it's important to ask. Just find out, what do you want? Do you guys want an Adobe RGB file? Do you want a CMYK PDF? Communication is the most important thing, is find out what they need. And a good print shop will know exactly what color profiles to use. They can tell you color profiles so you can proof it in advance. You can print it yourself, or you can look at it on your screen with a rendering of that color profile or whatever. So communication is the most important thing. All right, I used the term color profile a little bit on that last slide, mistakenly a little bit, but it is sometimes interchangeably used. It can be used interchangeably without too much confusion if you know what's going on. So we take a color mode or model. That's the big kind of all-encompassing color theory based on RGB or CMYK or LAB or whatever. And within that is going to fit a specific gamut, either device-dependent or device-independent color space. Now, color profile takes it down even smaller. It's not smaller necessarily, it's just more specific based on the device that's being used. So I can take a hardware device and I can stick it on my computer screen and run some software, and it's going to measure exactly what the characteristics are of my monitor's color output, which may be different from your monitor, which will be different from my iPad and my TV, and everything's going to have its own very specific color characteristics. And the measurement of those color characteristics is called a profile. So I can also take a similar hardware device and I can print off a sheet with a whole bunch of color patches on it, and I can run this hardware device over all of those little color patches, and it's going to measure exactly what color is coming out of my press or my desktop printer or whatever. And I can make a specific profile for that device. On print, it's going to make a difference depending on whether you're printing on newsprint or glossy paper or cover or text or matte or whatever type of paper you're using is going to have a big impact on that profile as well. So you'll have a profile for each device and each paper type that you're using, each substrate. So these are important because that profile is what's going to communicate to the RIP, to the software, to the monitor, to every piece of equipment in that workflow. It's going to communicate exactly how to interpret color, so that when The photographer takes a picture with a calibrated camera setup. He edits that picture on a calibrated monitor. He sends it on to the designer, who is going to then work on the file and prep it for different outputs and different types of substrates and screens. It's going to look the same to each person along the way. Then it's going to come to the print shop, and the print shop or the press is going to understand, based on that profile, exactly what's going on with the colors. This process of understanding color and keeping it consistent throughout the whole workflow is called color management. Color management is really critical in commercial printing. Most commercial printing is done for brands, for clients who have specific colors. Think of some of the big brands that you're familiar with. Coca-Cola comes to mind really quick because they have a very characteristic red. If that comes out in print for their packaging of, I don't know how many cans come in a pack, a 12-pack of soda, is that a thing? If that cardstock package on the soda cans is the wrong color of red, it's not going to fly. It's not going to pass muster with press checks, and they're not going to pay for those prints. So everyone along that chain needs to understand and implement color management so that the color turns out right from start to finish. Okay, so let's see. Color conversion is, like we said before, you're going from RGB to CMYK. It's going to pit stop in LAB because the math works better that way and it's more accurate. When you're converting colors, you want to avoid converting, or you want to avoid down converting from RGB to CMYK until the very end when it's in the delivery stage. So when you're going from the design files to the print files, that's when you would convert to CMYK. And again, communication between the designer and the print shop is critical there. When you are in Photoshop or InDesign or whatever, you can do something called soft proof. And soft proof is simply a way to preview how the print's going to look. Your screen, because it's RGB, it's got a gamut that can handle everything within CMYK. All it has to do is dim down and mute the colors a bit to show you exactly what it's going to look like when it's printed. Now, because your screen is emitting light, it's not reflecting light, just like a paper does, it's not going to be 100% perfect. The more expensive your monitor is and the higher quality it is and the more recently you've calibrated it and a lot of other on and on caveats, you can get it really, really close to where what you see on the screen is going to look very much like what you print. That's the whole basis of that working, is having an accurate color profile for your devices, having your devices calibrated, and having the correct profile in the document itself. All right. Channels. Channels are what they're called in Photoshop and software. Separations. We talked about that last week in Halftones. But your CMYK channels in Photoshop or whatever are going to be just the separations that would be made into different plates. Technology, or terminology, I should say, that I just wanted to throw in here and cover is RIP. This will come up occasionally. A RIP is a raster image processor. That's a server. In the case of a large press or digital press or something, it's going to be a server attached to the device in the print shop. Or you have a RIP in your, I'm sorry about that, click happy here. Or if you print to your desktop printer, you're going to have a driver that rips the image as well. So it's going to take the pixels, text, and everything else in your digital file. It's going to convert it to a whole bunch of dots and create a halftone pattern or a stochastic pattern that's going to go down on the paper as ink. The pixels in your image don't convert well into, if you printed directly the pixels of the image on the paper, then it would look terrible. And I'll show you. So here's the difference. So on your screen, you have pixels. It's a grid of squares, and each square is a solid color. As you can see on the image on the left-hand side there, you have this tiny little dot that has kind of some shading on it, three-dimensional, fake-looking, with some anti-aliasing, and on the left-hand side, that looks fine on the screen when you zoom out far enough, right? On the right-hand side, the difference is that all those pixels have to be converted into dots. And you'll notice that for every single pixel on the left-hand side, there's going to be a large number of dots that make up that pixel. Because if we have a dot, think back to CMYK, we have 3 colors and black to work with, right? Our pixel on the screen, we can have purple, which is going to be kind of a magenta and a blue mixed together, right? So to make that purple pixel match up, it's going to have a combination of cyan and some magenta and maybe a lot of white in between those dots. And so you're going to have a lot of information within the space that pixel took up in your digital file. So I'm looking right here at this purple. If we look over here at this is going to reproduce, and when we look at the file printed on paper at the right viewing distance, this is going to be our DPI over here. Dots per inch relates to how many dots fit in a certain space. Pixels per inch is a pixel in a certain space. So our dots per inch is typically going to be a lot higher than our pixels per inch. Now, dots per inch is not something that you set. And so you don't have to worry about, oh, what are my dots per inch? Do I need to have a certain number of dots per inch for this print? No, that's a characteristic of the printing device. So your output device, your printing press, is going to be capable of a certain number of dots per inch. So if you need more dots per inch, you're going to have to buy a new printer. So it's not something that you're necessarily going to change. Now, some of them you can choose how many dots per inch to print, but again, that's something that the print shop is going to need to solve for you. As a designer, you're going to be worrying about providing enough pixels so that they can get a high quality image printed. All right, so talking more about resolution here. Resolution is really just density of information. When we go back to pixels per inch, it's the density of pixels in a certain surface area. Lines per inch is another measurement of, let's see our slide. Okay, lines per inch is another measurement of how much information is in a certain area. However, it's a little different. Remember we talked about last time screens, the screen angles of our different separations. So cyan is going to go one angle, and then there's going to be a line of our yellows, and then a line of our magentas, and they're all in slightly different angles. And those angles are good. Just think back to that image because it illustrates the lines, the spacing of lines. Each one of these cells, if you look at the image on the left-hand side here, this halftone cell right here is made up of a bunch of lines. There's a grid. And the closeness of those rows or lines is our lines per inch. So that's going to vary depending on the type of press that you have. Certain presses are going to, and press technologies like flexography is going to be different from gravure, and web offset is going to be different from screen or whatever. Anyways, the LPI is going to be variable depending on the type of device that we're printing to. It's also going to depend on the type of substrate that we're using. We talked about newsprint before because it's a good example of a bad substrate, is that you can't print very high LPI on that type of substrate because the ink is going to absorb into the paper too much and bleed together. It's going to be a problem. So LPI, we can set our resolution in our document based on the LPI that our device and our substrate are capable of holding up to. So we'll look at this a little bit. I'll give you guys an assignment later on in the class that'll let you kind of experiment with LPI a little bit more. And hopefully it'll make more sense then. I just threw in some more halftone images to kind of bring into your awareness a little bit more of what's going on with those. So you look at this image and then go to the next slide and you see that's what we're looking at. Viewing distance is important. So we talked about resolution and having enough pixels or dots or lines per inch, but viewing distance is where it's critical. As a designer, if you're designing for print, everything doesn't have to be 300 pixels per inch in your file. Because let's say that you're printing something on a book. People are going to hold it inches to a couple of feet from their face probably, and the viewing distance is pretty close. You need to have high enough resolution that those individual dots like this aren't going to be distinguishable. You want the person to see the image where the colors actually start to blend together and you get the illusion of all those tones and colors and hues. However, think of like a billboard, for example. If you are designing something for a billboard, what's the viewing distance going to be of that? Definitely not going to be a few inches, not a few feet either. It's going to be 50 yards or further, and they're going to be passing it at 80 miles an hour on the freeway. So the viewing distance is much different. The dots are going to be much larger and further spaced. you can design at 24 pixels per inch, for example, instead of 300 pixels per inch, and you're going to have enough resolution based on the viewing distance that it's going to look just fine.